The question is now, what is the ith force? The answer, we already know it. The ith force is the total force applied to the ith particle. What we will do is that we will decompose this force into two components. The first component is the sum of all the applied external forces. That is labeled with the superscript of an A in parentheses. The other component are the forces of constraint acting on the particle. For example, if the particle is resting on a table, the normal force the particle feels due to the table pushing back is a force of constraint. If we replace this form of the force into the equation we ended last class with, we can see that the total work done by the system can be decomposed into two parts. We shall first look at the last term and then come back to the other one. Thus, if we first look at the second term, we can see that this is the work done by the constraint forces. We shall assume that the work done by the forces is zero. But why can we do this? We cannot just assume it out of the blues. This assumption comes from the fact that in many systems the movement is typically perpendicular to the constraint forces. In general, we will not consider systems where the constraint forces are parallel to the displacement, for example, friction. This is not always the case, but constraint forces that are parallel to the displacements tend to be non-conservative. Notice that we are also assuming internal forces that follow Newton's third law, so the combined work of the action and reaction pairs will yield a net work done of 0. Thus, this term by itself will be 0. This is called the principle of virtual work. A virtual displacement is a displacement such that the work done by a constraint force is 0. As an example, if a box is resting on a table and it is pushed so that it is moved, the normal force the particle feels due to the table pushing back does no work since the displacement is always perpendicular to the force. Now that we know that the internal forces do 0 net work, we can go back to our equation and remove the net work done by the internal forces. Thus, we get to the result known as D'Alembert's principle. It is from this principle that we will get Lagrange's equations. Getting Lagrange's equations from this principle is really not that hard, but it does require some mathematics that are beyond the scope of this course. In reality, it is not that hard, but it does take some time to digest. So, rather than going through the complete procedure, we should just look at some useful results and then summarize the procedure to get the results of interest. We will state three major results. The idea is to first introduce some notation. The functional dependence of several variables can be denoted by using set notation or vector notation, or more properly, array notation. These two types of compact notation you will usually find in advanced textbooks. The first result is that if the coordinate of the ith particle is written in terms of these parameters, then a small displacement to first order can be approximated by a first order Taylor series expansion in terms of the parameter variables. Notice that we don't include time, since we are assuming that we are looking for the coordinate path, not the time path. Notice that it is convenient to use Einstein's notation where a summation is performed over the variable k. To use D'Alembert's principle, we must also obtain the velocity of the ith particle in terms of the variables q and their derivatives. Notice that the velocity is the absolute derivative of the position with respect to time, so we must consider the partial derivative with respect to time of the position as opposed to the previous result. You can also use Einstein's notation and use simplified notation for the derivatives with respect to time. The q dots are called generalized velocities. The final assumption is that the systems we are considering are made up of point particles such that we can write the change in momentum with respect to time as the mass times the acceleration in vector form. We will now write the work done in terms of a generalized force that is represented by an uppercase Q sub k multiplied by the variation of the generalized coordinate lowercase q sub k. A generalized force is a variable such that when multiplied by the corresponding generalized coordinate in scalar form yields the quantity of work. For example, uppercase Q sub k might refer to a torque and delta Q sub k an angle. We can now use the three previous results. We will also assume that the force we are dealing with can be written as the gradient of a function. Very important warning, we have not assumed that this force is conservative. In general, this force need not to be conservative. Thus, the variable phi is not necessarily a potential energy function. In the case where phi only depends on the positions, this will be a potential energy function. If we define the kinetic energy to be the sum of all the kinetic energies, we need not to worry about further expanding the velocity v since it already depends on the parameters, so no further manipulation is needed other than the one in the previous segment. Considering the previous results, we can write D'Alembert's principle in terms of the Q parameters. We could stop at this equation, but we can go further if we make more assumptions. Now, assuming that the force can be written as the gradient of some function phi that is not necessarily a potential energy function, we can simplify the expression for the generalized force For this, we have used the chain rule. Thus, we can write D'Alembert's principle as Notice that all the vectors have disappeared and we are left with the kinetic energy of the system T and the function phi, both as functions of the parameters and their derivatives. Thus, for this expression to be zero, each term in the summation that is multiplied by a parameter delta q sub k must be zero, since delta q sub k is an arbitrary displacement. If the function phi does not depend on time and in the time derivatives of the parameters q, that is, phi is a potential energy function, then we can write the equation for the jth particle as the derivative of the kinetic energy T minus the potential energy function phi. This quantity, T minus phi, is called the Lagrangian function. In general, we can define the Lagrangian of a system as a function of the derivatives with respect to time of the generalized velocities, generalized coordinates, and time. For conservative forces, phi is the potential energy function. Thus, for every independent generalized coordinate, there is a differential equation that determines the functional form of the generalized coordinate, and, in general, these differential equations are coupled, meaning that they may be related to each other, as it is usually the case. These are called the Euler-Lagrange equations of the system, or just Lagrange's equations. Notice that this equation is similar to that of the calculus of variations, but by replacing x by t. The resulting function is s, and it's called the action. It is defined as the integral of the Lagrangian function between two fixed times. The Lagrangian function is a function of the generalized coordinates, or the q-parameters, their time derivatives, and time. The name for this is called Hamel's principle for classical mechanics, and it was the starting point for Emmy Noether to demonstrate her famous theorem. Notice that Lagrange's equations can be obtained by extremizing s. The only caveat is that this can only be done so if the constraints are holonomic. That implies independence of variables. Also, notice that the equations do not give us the constraint forces. The constraint forces that must come from holonomic constraints are obtained by using Lagrange multipliers. This is a topic that I will briefly explain in the problems we will solve, but it is somewhat beyond the scope of what was intended to be covered. The big question is, how do we implement this principle to get Newton's equations? For this, I will provide some handwritten notes through Moodle. Please make sure to review this content for the final exam, since it will be a big part of it.